Tonight, we are going to start with something you have probably never thought to question. Everything spins. Not most things. Not things under certain conditions or at certain scales. Everything. Every planet you have ever heard of is rotating on its axis. Every moon orbiting every planet is rotating. The sun is rotating. Every other star in the Milky Way is rotating. The Milky Way itself is rotating. Every galaxy we have ever observed is rotating. Electron spin, proton spin, neutron spin. The quarks inside those protons and neutrons spin. Even neutrinos, the ghost particles so lightweight that a light year of solid lead would stop fewer than one in a quadrillion of them, have a spin. We can measure that spin. We use it to tell different types of neutrinos apart. Tonight, we're going to follow that spin from the very largest structures in the observable universe down to the smallest things that physics can describe. We're going to visit rotating galaxy clusters, the flat spinning disks of individual galaxies, the protoplanetary disk that built every planet in this solar system, the tidal forces that are slowing Earth's rotation right now and pushing the moon an inch and a half farther away every single year, the neutron stars that spin hundreds of times per second and keep time more precisely than any atomic clock ever built, the black holes that drag space-time itself around with them as they rotate, and the quantum world where spin turns out to be something so strange that the word itself is almost misleading. By the end of tonight, we will have a real answer to where all of this rotation comes from. Not a metaphor, a physical chain of cause and effect, tracing every spinning thing in the observable universe back through 13.8 billion years of history to a single print. By the end of tonight, you will understand why the spin of the Milky Way and the spin of an electron are not two separate phenomena that happen to share a name. They are the same phenomenon, expressed at enormously different scales, through enormously different mechanisms, but conserved by exactly the same law all the way down. We make long, form-sleep documentaries about space and cosmology. We try to cover the science as carefully as we can and make each one worth the time you give it, even knowing that most of you are here because you will not be awake for much of it. If tonight is your first time with us, the link in the description will bring you back. There is a lot more where this came from. Now, let's begin. The first thing to establish is that spin, in physics, is not merely an observation that was catalogued and filed away. It is a conserved quantity. Being a conserved quantity is one of the most precise and powerful things a physical quantity can be. It means the laws of physics protect it so completely that, in any isolated system, it can never be created from nothing, and it can never simply cease to exist. You can transfer it from one object to another. You can redistribute it, but you cannot make it vanish. The formal name is angular momentum, and the reason it is conserved is not something physicists discovered by watching enough spinning things. It is a mathematical consequence of something far deeper. In 1918, a German mathematician named Emmy Noether proved one of the most important results in the history of physics. Her theorem states that every conservation law in nature corresponds to a symmetry of the laws of nature. Symmetry here has a precise technical meaning. A symmetry is a transformation you can apply to a physical system that leaves the laws governing that system entirely unchanged. Energy is conserved because the laws of physics are the same today as they were yesterday. Shift any physical system forward in time by a day or a year and run the same experiment. The same equations govern the outcome. The laws are symmetric under time translation. Because of that symmetry, Noether's theorem says, energy cannot be created or destroyed. Linear momentum is conserved because the laws of physics are the same here as they are 3 feet to your left. Move your experiment across the room, and the same equations apply. The laws are symmetric under spatial translation. Because of that symmetry, momentum cannot be created or destroyed. An angular momentum, the thing we call spin, is conserved because the laws of physics are the same regardless of which direction you face. Rotate your coordinate system by any angle, and the same equations govern everything. The laws are symmetric under rotation. This symmetry is called isotropy. It means the universe has no preferred direction. There is no orientation that the laws of physics care about more than any other. And because of that isotropy, angular momentum is as inviolable as the laws of physics themselves. This is not a rule the universe decided to follow that it could in principle break. It is a mathematical theorem that follows necessarily from the fact that space has no special direction. If the laws of physics are the same in every direction, and every experiment ever performed confirms this, then angular momentum is conserved. There is no version of the laws of physics in which it is not. No one expects the conversation about why planets rotate to begin with a theorem about the mathematical symmetry of physical law proved in 1918. But it does. Everything else we discussed tonight is an application of Noether's theorem to different systems at different scales. The spinning gas clouds that form solar systems, the rotating disks that become galaxies, the collapsing stellar cores that become neutron stars, the intrinsic angular momentum of every fundamental particle. All of it, one theorem expressed at every scale. Before we leave this principle and move to the concrete cases, it is worth sitting with what it really means. The universe did not look around, see that things were spinning, and decide to keep them spinning. The universe has no preferred direction, and the consequence of having no preferred direction is that angular momentum cannot be created or destroyed. The conservation is not a policy. It is the mathematical shadow of an absence of any special direction, an absence of any preferred orientation. The universe treats all directions the same, and the cost of treating all directions the same is that rotation is permanently conserved. Everything spins because the universe began with a certain amount of rotation and has had no mechanism, no law, no force that could remove it. 13.8 billion years on, and the spin is still exactly there, in every electron, in every neutron star, in every rotating galaxy, precisely accounted for. Let us now turn to the solar system, where the consequences of angular momentum conservation first became physically visible. 4.6 billion years ago, where the solar system now sits, there was a molecular cloud, a loosely gravitationally bound collection of gas and dust drifting through what would become the outer disk of the Milky Way. It was cold, around 10 Kelvin, just barely above absolute zero. It was enormous, probably spanning several light years at its widest extent, and it was not perfectly still. Nothing in the universe is perfectly still. The Milky Way rotates, and differential galactic rotation produced shearing forces across the cloud. Nearby massive stars blasted it with ultraviolet radiation and energetic stellar winds. Earlier generations of dying stars had sent shock waves through the interstellar medium, some of which had passed through this cloud and deposited pressure variations inside it. The cumulative effect of all of these interactions was that the cloud had a very slight net rotation, a barely measurable preference for spinning in one direction rather than another. Barely measurable is the key phrase. Before the collapse, the rotation was so slow that if you had been floating inside the cloud, you could not have detected it without instruments of extraordinary sensitivity. Then something triggered a collapse. The leading candidate, supported by isotopic ratios measured in meteorites that formed from this same cloud, is a nearby supernova, a massive star that ended its life catastrophically and sent a shock wave through the interstellar medium. When that shock wave reached the molecular cloud, it compressed one region past the threshold where gravity could no longer be resisted. The cloud began to fall inward. Here is where angular momentum conservation takes over, with what can only be described as mathematical relentlessness. Think about a figure skater. She is spinning slowly with her arms extended. When she pulls her arms in close to her body, she spins faster. Her mass stays the same. Her total angular momentum stays the same. But angular momentum is proportional to mass times the square of the radius of rotation times the angular velocity. If the radius decreases by a factor of 2, the angular velocity must increase by a factor of 4 to compensate. If the radius angular velocity increases by a factor of 100, the collapsing gas cloud did the same thing, but instead of arms pulled in over a distance of a few feet, it was billions of tons of hydrogen and helium gas falling inward over a distance of light years. The faint, barely detectable rotation of the original cloud, compressed into a volume tens of millions of times smaller, became a rapidly spinning disk. The disk shape is not arbitrary, and it is not a coincidence. It is the geometrically inevitable consequence of angular momentum acting on a self-gravitating collapsing system. Matter falling in along the rotation axis, the north and south poles of the spin, has no angular momentum component perpendicular to the axis. It can fall all the way to the centre with relatively little resistance. But matter falling in at the equatorial plane has to fight the centrifugal effect of its own angular momentum. As it falls inward, the outward push of its own rotation grows. It cannot fall all the way to the centre. It settles into the plane, into a disk. The disk is the lowest energy configuration for a rotating, self-gravitating system under these conditions. Gas clouds under gravity with net angular momentum do not form spheres. They cannot. They form disks. This is why the solar system is almost entirely flat. The 8 planets orbit in planes tilted by less than a few degrees relative to each other. The asteroid belt lies in the same plane. The Kuiper belt, the population of icy bodies beyond Neptune, lies in roughly the same plane. All of it is a record of the original disk, a direct imprint of angular momentum conservation on the structure of the solar system. In the centre of the disk, the density and temperature rose until hydrogen began fusing into helium. The sun ignited. In the surrounding disk, the remaining material clumped, dust grains sticking to other dust grains under electrostatic forces, pebble-sized grains accumulating into boulder-sized objects, boulders sweeping up more material gravitationally until they became planetesimals hundreds of miles across, and planetesimals growing into the full planets that orbit today. Because all of this material was born from the same rotating disk, it all inherited the same direction of angular momentum. The planets orbit the Sun counterclockwise when viewed from the solar system's north pole. Most of them rotate counterclockwise. Their moons orbit counterclockwise. The entire architecture of the solar system is a fossil record of the original rotation of the molecular cloud that built it, amplified by gravitational collapse, written in the orbits of worlds. Expectation. Every planet should rotate in the same direction, roughly in the plane of the solar system, reflecting uniform angular momentum inheritance from the protoplanetary disk. Reality. Venus rotates backward, Uranus rolls on its side, and Earth's own rotation is slowing down right now at a measurable rate. Let us take these one at a time. Venus rotates in the direction opposite to every other planet. When viewed from the north, it rotates clockwise, what is called retrograde rotation. It rotates so slowly that a single Venusian day, measured from one sunrise to the next on the surface, lasts longer than a Venusian year. One full orbit of the Sun takes 225 Earth days. One full rotation takes 243 Earth days. The planet completes an orbit before it completes a rotation, and the rotation is running in the wrong direction. The leading explanation is a large impact, very early in solar system history, while Venus was still young and partially molten. A body massive enough to reverse the planet's spin struck it at the right angle. We cannot observe this impact directly. We can only observe its aftermath. But the same models that explain the formation of the Moon from the Theia impact predict that large impactors were routine in the early solar system, when planet-scale bodies were still roaming on uncircularized orbits. A retrograde Venus is not a puzzle requiring special physics. It is the expected outcome of a formation environment violent enough to build planets from collisions. Uranus tells a similar story. It is tilted 98 degrees from the perpendicular to its orbital plane, meaning it rotates essentially on its side, with its poles pointing nearly at the Sun at certain points in its orbit. Its rings and moons orbit in the plane of its tilted equator rather than the plane of the solar system, which tells us the tilt happened before the moons formed. The system reoriented and then rebuilt itself in the new orientation. Again, the leading explanation is an early large impact, one that tipped the planet on its side before its moons had time to accumulate from the surrounding disk. These anomalies are sometimes described as problems for the angular momentum story of solar system formation. They are not. They are confirmation that the early solar system was a place of enormous violence, and that angular momentum conservation operated throughout. The total angular momentum of Venus plus whatever struck it is the same after the collision as before. The collision redistributed it, leaving a retrograde Venus. The total angular momentum of the Uranus system before and after the tipping impact is the same. The redistribution just looks surprising when you examine the aftermath alone, without knowing the history. No one predicts that the direction of a planet's spin would encode the most violent event in its history, but it does. The rotation of every planet is a record of every major impact it has experienced. Now let us talk about Earth's own rotation, because it is far richer than most people know, and because it gives us the clearest possible demonstration of angular momentum conservation operating on something we can actually measure. When the Earth formed 4.5 billion years ago, it was rotating much faster than it does today. The early Earth completed a full rotation in somewhere between 6 and 12 hours. The precise figure depends on what happened very shortly after formation, because Earth's rotation was fundamentally altered by the largest impact in its history. Roughly 50 to 100 million years after the solar system formed, a body approximately the size of Mars struck the Earth. The impactor is called Theia, named for a figure in Greek mythology. The collision was a glancing blow, not a direct head, on impact. It was so energetic that both bodies were partially vaporized. The mixed debris of the two objects either fell back onto the growing Earth or went into orbit around it. Over the next few thousand years, the orbiting material accumulated into the Moon. In the aftermath of the Theia impact, the Earth-Moon system had a specific total angular momentum. It included Earth's rotation, the Moon's orbital motion around Earth, and the Moon's own rotation. That total angular momentum has not changed in 4.5 billion years. What has changed continuously and measurably is how it is distributed between those three motions. The mechanism of redistribution is tidal forces. The Moon's gravity does not pull on every part of Earth with equal strength. It pulls on the side of Earth facing it slightly more strongly than it pulls on the far side, because gravity weakens with distance, and the near side is simply a bit closer. This differential pull creates a slight stretching of Earth, a tidal bulge on the side facing the Moon, and a smaller tidal bulge on the opposite side. The Moon is pulling the near side toward it and effectively pulling the far side less strongly, so it bulges outward in the opposite direction. Earth rotates under this tidal bulge. The solid rock of Earth's mantle is being continually deformed, stretched into the bulge on one side, then carried away as Earth rotates, then stretched back toward the bulge again as it comes back around. This continuous deformation generates heat, dissipated in Earth's interior and in the friction of the tides in shallow seas, and as it does, it robs Earth's rotation of energy. But here is the critical point. Earth's rotation slows. The angular momentum extracted from Earth's spin does not disappear. It cannot by Noether's theorem. It is transferred to the Moon. Specifically, it goes into the Moon's orbital angular momentum. The Moon accelerates slightly in its orbit, which pushes it into a higher, larger orbit. Earth slows down. The Moon moves outward. The rate at which Earth's day is currently lengthening is roughly 1.4 milliseconds per century. That sounds completely negligible. Over 4.5 billion years, it adds up to a difference of 18 hours between the early Earth and today. We have direct evidence for this. Ancient fossil corals, which lay down daily and seasonal growth rings just as trees do, show that roughly 400 million years ago, a year contained about 400 days instead of 365. Each day was shorter than today by roughly 21 minutes. The Earth was rotating faster. The fossil corals are a record of Earth's angular momentum, written in calcium carbonate laid down one layer per day. The Moon is currently about 238,000 miles from Earth. We know this with extraordinary precision, to within a centimetre or less on any given day, because the Apollo missions placed retroreflectors on the lunar surface, and we have been measuring the round trip travel time of laser pulses bounced off them for more than 50 years. From these measurements, we know the Moon is moving away from Earth at roughly 1.5 inches per year. The retroreflectors placed by astronauts in 1969 are about 200 feet farther from Earth now than they were when placed, not because the Moon is being pushed away by some force, but because Earth's rotation is slowing and the angular momentum flows to the Moon's orbit. No one expects our most precise knowledge of the Moon's distance to come from mirrors left by astronauts in 1969 that are still being used today. But the physics is direct. Angular momentum flows from Earth's spin to the Moon's orbit, and the laser ranging measurements watch that flow in real time to millimetre precision. This tidal process has a natural endpoint. It is already visible in the Moon itself. The Moon rotates once for every orbit around Earth, always showing us the same face. This is called tidal locking. The same tidal mechanism that is currently slowing Earth completed its work on the Moon billions of years ago, when the Moon was younger and more easily deformed. The Moon's rotation slowed until it matched its orbital period exactly. Now it is frozen there in angular momentum equilibrium with Earth's gravity. The far side of the Moon, which no human eye ever saw until a Soviet spacecraft flew past it in 1959, exists because tidal locking is real and angular momentum was transferred from the Moon's rotation to its orbital motion until the two were synchronized. The future of Earth is the same. Given enough time, Earth's rotation will slow until it is also tidally locked to the Moon, always showing the same face to it. At that point, the total angular momentum of the Earth Moon system will still be exactly what it was at the moment of the Theia impact. Not a unit more, not a unit less. It will simply be stored almost entirely in the orbital distance between Earth and Moon, with virtually nothing left in either object's rotation. Tidal locking is the universal outcome for any small body in close orbit around a large one, given sufficient time. Mercury is not yet tidally locked to the Sun, but is caught in a 3.2 orbital resonance, rotating 3 times for every 2 orbits, a halfway state on the road to the 1.1 lock that is the final equilibrium. The Galilean moons of Jupiter, Io, Europa, Ganymede, and Callisto are all tidally locked to Jupiter, rotating once per orbit. Most of Saturn's major moons are similarly locked. Pluto and its large moon Charon are mutually tidally locked, both always showing the same face to each other permanently across 12,000 miles of space. In every case, angular momentum moved between rotation and orbital motion until the system found a lower, energy equilibrium. The total was always conserved. By the end of tonight, we will see this pattern repeated at scales far larger than Earth and Moon. Angular momentum redistributes. It never disappears. Now let us move outward from the solar system to the galaxy. The Milky Way is a barred spiral galaxy, roughly 100,000 light years across. The Sun sits roughly 26,000 light years from the galactic center, orbiting it at roughly 514,000 miles per hour. At that speed and distance, one full orbit takes roughly 225 to 250 million years. This unit of time is sometimes called a cosmic year or a galactic year. To give that timescale some context, the Cambrian explosion, when complex animal life first diversified explosively in Earth's oceans, happened roughly 540 million years ago. In that time, the Sun has completed slightly more than 2 full orbits of the galaxy. The entire known history of complex animal life on Earth spans about 2 galactic years. Every star in the Milky Way's disk orbits the galactic center, in the same counterclockwise direction when viewed from the North Galactic Pole. Not approximately the same direction. The same direction. This organized, coherent rotation of hundreds of billions of stars all orbiting in one direction is not a coincidence, any more than the planets of the solar system all orbiting in one direction is a coincidence. It is angular momentum inheritance. The Milky Way disk formed the same way the protoplanetary disk formed, with a cloud collapsing and conservation of angular momentum amplifying the original rotation into a flat, spinning structure. The stars of the disk inherited that rotation. But here is where the galactic story diverges from the solar system story in a way that changed our understanding of the universe. In the solar system, orbital speed decreases with distance from the Sun, just as Kepler's laws predict. Mercury orbits at 107,000 miles per hour, Jupiter at 29,000, Neptune at 12,000. The gravitational force weakens with distance, and so the speed required to maintain a circular orbit also weakens with distance. Expectation: galaxy rotation curves should look the same. Stars close to the galactic center should orbit fast. Stars progressively farther out should orbit progressively slower, following the same mathematical relationship we see in the solar system. Reality, they do not. In the 1970s, an astronomer named Vera Rubin, working at the Carnegie Institution in Washington, began systematically measuring the rotation curves of spiral galaxies, determining how fast stars at different distances from the galactic center were orbiting. The result was not what anyone had predicted. The rotation curves of spiral galaxies are nearly flat. Stars at the outer edges of galaxies orbit at almost the same speed as stars at intermediate distances. In some cases, the outermost stars orbit slightly faster than expected based on the visible matter alone. The speed does not fall off with distance. It stays roughly constant far beyond where the visible disk of stars ends. This was not a measurement error. Rubin measured it consistently across dozens of galaxies. Other astronomers reproduced her results. The flat rotation curves were real. Flat rotation curves were physically impossible if the only mass in the galaxies was what we could see. If the visible stars and gas were all the mass present, the outer stars would be moving too fast to remain in circular orbits. The gravitational force at those radii, from the visible matter, would not be sufficient to keep them on their paths. They would fly outward. The galaxies would be tearing themselves apart. They were not tearing themselves apart. The only physically consistent explanation was that there is far more mass in galaxies than we can see, mass distributed not in the disk but in a vast, roughly spherical halo surrounding the entire visible galaxy, massive enough that its gravitational pull keeps the outer stars on their circular orbits. This mass does not emit light. It does not absorb light. It interacts with ordinary matter only through gravity. It is dark matter. No one predicts that measuring the rotation of galaxies would reveal an invisible form of matter that outweighs all the stars, gas, and dust in the observable universe by a factor of roughly 5 to 1. But that is what flat rotation curves imply, and every subsequent line of evidence has confirmed it. The Bullet cluster, a pair of galaxy clusters that collided and passed through each other, gave perhaps the most vivid confirmation. The hot gas of each cluster, which contains most of the cluster's ordinary mass, was slowed by electromagnetic drag during the collision and lagged behind the galaxies. Gravitational lensing maps of the system, which show where the mass is by how the cluster bends background light, showed the mass concentrated not where the gas had ended up but where the galaxies were, having passed through each other without slowing. The dark matter had passed through the collision freely, interacting only gravitationally, exactly as predicted. The Planck satellite's final results from the cosmic microwave background give the composition of the universe to remarkable precision. Roughly 5% ordinary matter, the atoms and molecules we know, 27% dark matter, and 68% dark energy. The matter we can see, every star and planet and gas cloud and nebula, is the minor constituent of the universe's matter budget, Dark matter is the dominant form, and we first inferred its existence by studying the rotation of galaxies. No one expects the study of spin to reveal the composition of the universe. But Vera Rubin's flat rotation curves are what took us there. The dark matter halo does not participate in the disk's organized rotation the way the stars do. It is roughly spherical, not a disk, and its constituent particles orbit in a swarm of individually random but collectively stable trajectories, rather than all going around in one direction. But the halo's gravity is what makes the disk's rotation pattern possible. Without the dark matter halo, the disk would not be stable. The angular momentum of the full galaxy, disk plus halo, is more complex than the solar systems, but the conservation law is exactly the same. Now let us ask where the Milky Way's angular momentum came from in the first place. The oldest stars in the Milky Way, found in the ancient globular clusters and the stellar halo, are roughly 12 to 13 billion years old. They formed within the first billion years of the universe's history, during the chaotic early collapse of the protogalactic system. The disk stars, including the Sun, formed later as the remaining gas settled into the organized disk structure dictated by the net angular momentum of the protogalactic cloud. That protogalactic cloud's angular momentum came from tidal torquing. As the cosmic web of filaments, sheets and voids assembled from the density fluctuations of the early universe, matter flowed along filaments toward the dense intersections where galaxy clusters would form. The Milky Way formed at one such node. Material was flowing into the protogalactic region from multiple directions, along multiple filaments. But those filaments were not perfectly symmetric. More material arrived from one direction than from directly opposite. The tidal field of the surrounding large-scale structure was slightly asymmetric around the forming galaxy. That asymmetry torqued the infalling material into rotation. An asymmetric tidal field acting on a collapsing object imparts angular momentum to it. This is tidal torquing, and it is the mechanism by which the cosmic web transfers angular momentum to galaxies. The tidal field traces back to the distribution of matter in the early universe. The distribution of matter traces back to the density fluctuations seeded during inflation. The density fluctuations were quantum mechanical in origin. The unavoidable probabilistic variations in the energy density of the inflaton field that drove the exponential expansion of the very early universe. The rotation of the Milky Way, the 514,000 mile per hour orbit of the Sun around the galactic center, traces causally to quantum fluctuations in the first fractions of a second after the Big Bang, not as a poetic connection, as a direct, unbroken physical chain. Tonight we have talked about the spins of planets in our own solar system, as though they were the only planets we know. They are not. As of the early 2020s, astronomers have confirmed more than 5,500 planets orbiting other stars, with many thousands more candidates awaiting confirmation. And the spin of these distant worlds, their orbits and rotation axes relative to their parent stars, has revealed something important about the universality of what we have been discussing. By the end of tonight, we want to note one of the most striking facts in exoplanet science. A significant fraction of the planets in other star systems orbit in ways that have no analogue in our solar system. Some orbit in the opposite direction to their star's rotation. Some orbit in planes that are nearly perpendicular to the stellar equator. Some orbit so close to their stars that they complete an orbit in less than a day. These are called hot Jupiters, gas giants orbiting where Mercury would be burned to a cinder, and they raise exactly the same question as Venus's retrograde rotation. What redistributed the angular momentum? The measurement technique that reveals the alignment between a planet's orbit and its star's rotation is called the Rossiter-McLaughlin effect. When a planet transits its star, moving across the face of the star as seen from Earth, it blocks a small fraction of the starlight. But the star is rotating, meaning one side of the star is moving toward us and the other is moving away. This rotation Doppler shifts the light from each part of the star's disk. The approaching side appears slightly blue, shifted. The receding side slightly red, shifted. When the planet blocks the approaching half of the disk, it removes blue, shifted light, making the whole star appear slightly red, shifted. When it blocks the receding half, it removes red, shifted light. The sequence of colour shifts during the transit traces the path of the planet across the stellar disk, and reveals whether the planet's orbital plane is aligned with or tilted relative to the stellar equator. No one predicts that the wobble in a star's colour during a planetary transit would tell us the history of that planet's migration. But the Rossiter-McLaughlin effect has now been measured for hundreds of transiting planets, and the results are striking. In our solar system, all the planets orbit within about 7 degrees of the Sun's equatorial plane. The solar system is well aligned, but many exoplanet systems are not. Some hot Jupiters orbit their stars in planes tilted 30, 60, even 90 degrees from the stellar equator. Some orbit in a retrograde direction, going the wrong way around their star relative to the star's rotation. These misalignments are the signature of violent dynamical histories. A planet does not naturally form in an orbit tilted perpendicular to its disk. It forms aligned with the disk, just as planets in our solar system formed aligned with the protoplanetary disk. For a planet to arrive in a misaligned orbit, something had to redirect its angular momentum after formation. The leading candidates are gravitational interactions with other planets in the same system, which can throw planets onto highly elliptical orbits that subsequently circularize through tidal interaction with the star but retain the tilted orbital plane, and gravitational perturbations from distant stellar companions in binary or triple star systems, which can tilt orbital planes through a secular oscillation called the Kozai-Lidov mechanism. The Kozai-Lidov mechanism deserves a moment's attention because it is a beautiful example of angular momentum redistribution across a complex system. In a hierarchical triple system, 2 objects in a close orbit with a third more distant body, the distant body's gravity exerts a long-term secular torque on the inner orbit. Over very long timescales, this torque causes the inclination of the inner orbit to oscillate, sometimes growing to very large values while the eccentricity also oscillates in a correlated way. The orbit's angular momentum is being exchanged between the inclination and the eccentricity, with the total angular momentum remaining conserved. The result can be that a planet originally in a nearly circular aligned orbit is gradually driven into a highly inclined, highly eccentric orbit by the gravitational influence of a distant stellar companion, then circularized by tidal interaction with the host star into a close, misaligned orbit. This mechanism has been invoked to explain many of the most extremely misaligned hot Jupiters. The planet Hat, P7b, a hot Jupiter orbiting the star Hat, P7, about 1,000 light years from Earth, orbits in essentially the retrograde direction relative to its star's rotation. Its orbital angular momentum vector points in almost exactly the opposite direction to the star's spin angular momentum. The total angular momentum of the system is conserved, but it has been redistributed over billions of years of gravitational interaction into a configuration that looks almost like the mirror image of what the planet started with. No one expects a planet to orbit its star backward, but angular momentum redistribution through gravitational interaction has no preference for aligned configurations. It moves angular momentum to wherever the least energy configuration lies for a given set of gravitational influences. Sometimes that lowest energy state is an aligned circular orbit like the Earth's. Sometimes it is a retrograde, close, in orbit like Hat P7b's. Tonight, the inventory of exoplanet spin and orbital architecture has expanded our picture of what angular momentum conservation produces across the full range of planetary system histories. Our solar system, with its well-aligned planets and its relatively gentle dynamical history, is not the universal template. It is one outcome among many, produced by a particular initial angular momentum distribution and a particular history of gravitational interactions. By the end of tonight, the spin of every world in every star system traces back to the same source, the angular momentum inherited from the disk that formed it, redistributed over billions of years by the relentless and perfectly conserving mechanics of gravity. Different histories produce different configurations. The law is the same in every case. Tonight we want to stay with dark matter for a moment longer, because what Vera Rubin's flat rotation curves revealed is not just that there is invisible mass in galaxies, it is that the dominant form of matter in the universe is something we have never directly detected and do not understand at the level of fundamental physics. By the end of tonight, we will have encountered angular momentum at every scale from quarks to galaxy clusters. But the dark matter discovery stands out among these because it came entirely from the study of rotation, not from a telescope looking at individual stars, not from a particle accelerator, from measuring how fast things were spinning. The leading candidate for what dark matter is made of, at least as of the past several decades of theoretical work, has been a class of particles called weakly interacting massive particles, or WIMPs. A WIMP would be a particle with a mass somewhere in the range of 10 to a few thousand times the proton's mass, interacting with ordinary matter only through gravity and the weak nuclear force. WIMPs were attractive theoretically, because several extensions of the standard model of particle physics, most notably supersymmetry, predicted particles with exactly those properties for independent reasons. The convergence of the particle physics motivation and the cosmological need seemed too convenient to ignore. From the 1980s onward, physicists built a series of increasingly sensitive detectors to search for WIMP dark matter directly. The strategy is straightforward in principle. If the Milky Way is embedded in a dark matter halo, then dark matter particles are presumably passing through Earth continuously. Occasionally one of them should collide with an atomic nucleus in a detector, transferring a tiny amount of energy in a nuclear recoil. By building detectors of increasing mass and sensitivity, shielded from cosmic rays and natural radioactivity deep underground, physicists hope to detect these recoils. The LUX experiment, operating in the Sanford Underground Research Facility in South Dakota in the 2010s, found nothing. Its successor, LUX Zeppelin, operational since 2022 and roughly 10 times more sensitive, has also found nothing. The Xenont experiment in Italy, operating a detector containing roughly 5 tons of liquid xenon a mile underground in the Gran Sasso Massif, has found nothing. The Pandax 4T experiment in China has found nothing. Each experiment has pushed the sensitivity deeper into the parameter space where WIMPs were predicted to exist. Each has come up empty. The absence of a WIMP signal does not prove that WIMPs do not exist. The particles might interact more weakly than the optimistic prediction suggested, putting them below the current experimental threshold. Or the mass might be at the edges of the range being searched. But the null results have substantially narrowed the space where WIMPs can hide, and have led many physicists to broaden their theoretical horizons. The other major dark matter candidate is the axion. Axions were proposed in 1977 by the physicists Roberto Pache and Helen Quinn to solve an apparently unrelated problem in quantum chromodynamics, the theory of the strong nuclear force. The strong force has a free parameter governing how much it violates matter, antimatter symmetry, and observations tell us this parameter is very close to zero, much closer than any natural explanation would suggest. Pecky and Quinn proposed a mechanism that dynamically drives this parameter to zero, and the axion is the particle that results from that mechanism. Axions, if they exist, would be very light, far lighter than WIMPs, and would interact with ordinary matter even more weakly. Detecting them requires different strategies than WIMP detectors. The ADMX experiment, the axion dark matter experiment, searches for axions converting to photons in a strong magnetic field inside a tuned microwave resonant cavity. The Abracadabra experiment and the Casper experiment use different approaches. None has detected an axion yet, but the parameter space being explored is expanding. No one predicts that the hunt for the particles that hold galaxies together via the flatness of their rotation curves would unfold over 40 years without a detection. But the universe does not arrange itself for our convenience, and the rotation of galaxies remains our clearest evidence that dark matter exists, whatever it turns out to be. Tonight, we should also note that some physicists have proposed an alternative, modifying the laws of gravity rather than adding invisible matter. Modified Newtonian dynamics, or MOND, proposed by Mordechai Milgrom in 1983, adjust Newton's gravitational law at very low accelerations of the kind that prevail at the outer edges of galaxies. MOND reproduces the flat rotation curves remarkably well without needing any dark matter. In fact, MOND makes a prediction called the baryonic-Tully-Fisher relation, a precise mathematical relationship between the total ordinary mass of a galaxy and the plateau velocity of its rotation curve. This relationship holds across galaxies spanning several orders of magnitude in mass, and MOND predicted it before it was precisely measured. But MOND has serious difficulties. It does not naturally explain the bullet cluster, where the mass inferred from gravitational lensing is spatially separated from the mass in the hot gas, exactly as dark matter predicts, and as MOND struggles to accommodate. It does not have a satisfactory relativistic generalization, and the CMB acoustic oscillations, the pattern of temperature fluctuations in the early universe on various angular scales, are beautifully explained by the standard dark matter model, and are very difficult to explain with modified gravity alone. The situation as of the late 2020s is that dark matter is still the leading hypothesis, the bullet cluster and the CMB remain its strongest evidence, the particle nature of dark matter is unknown, and every dedicated search for the most well-motivated particle candidates has come up empty. We know it exists. We know it is approximately 5 times more abundant than ordinary matter. We know it does not interact electromagnetically, and we know we found it, in the first instance, by measuring the spin of spiral galaxies and noticing that the stars at the edges were moving too fast. By the end of tonight, the image we want to leave you with is not one of unsolved mysteries, but of extraordinary detective work. The rotation of galaxies, a measurement that seems as prosaic as timing how fast a record spins, was the thread that pulled on the fabric of physics and revealed that we had been missing the majority of the universe's matter since the day we began doing cosmology, all because the stars at the edges of galaxies were spinning too fast. Tonight, we do not know what dark matter is, but tonight, we know exactly how we found out it was there. Stars form from molecular clouds, the cold, dense regions of the interstellar medium, where temperatures are low enough for hydrogen to form molecules rather than remaining as atoms, and where the density is high enough for gravity to eventually overcome thermal pressure. The nearest major star forming region to Earth is the Orion Molecular Cloud Complex, about 1,350 light-years away. The Orion Nebula we see with naked eyes or binoculars is a cavity blown in the front face of that cloud by the radiation, and winds from young massive stars that formed inside it about 3 million years ago. When a dense clump within a molecular cloud reaches the critical mass, called the Jeans mass, above which its own gravity can no longer be resisted by the thermal pressure of the gas, a gravitational collapse begins. The Jeans criterion depends on the temperature and density of the cloud. Cooler, denser regions become gravitationally unstable at lower masses. The coldest molecular clouds can form stars from clumps of only a few solar masses. Warmer, more diffuse regions require more mass before collapse begins. As the clump falls inward, the same physics as the protoplanetary disk formation operates, scaled to the mass of a star. Conservation of angular momentum amplifies the original faint rotation of the cloud fragment into a rapidly spinning protostellar disk. The protostar forms at the center. The remaining material in the disk is what eventually becomes planets, if the protostar is not too massive. But here is where something important happens that has no good analogue in the solar system. Angular momentum sometimes prevents a single star from forming. For a molecular cloud clump with very high angular momentum, the disk that forms may not be stable as a single structure. Instead, it fragments. Two or more density peaks grow within the disk, each collapsing to form its own protostar. The result is a binary or multiple star system. Roughly half of all solar-type stars in the galaxy have one or more stellar companions, bound gravitationally in binary or multiple star systems. The mechanism by which a single collapsing cloud produces two or more separate stars is, in most cases, angular momentum. The cloud had more angular momentum than a single star could hold, so the angular momentum manifested as orbital motion between two stars instead. In a binary system, the two stars orbit their common centre of mass, just as the Earth and Moon orbit their common centre of mass. The orbital motion carries the angular momentum that the original cloud had, distributed now between the two stars' orbital velocities and their own rotation rates. Close binary systems, where the two stars orbit within a few stellar diameters of each other, experience strong tidal forces from their mutual gravity. The same mechanism that is slowing Earth's rotation and pushing the Moon outward operates between two stars in a binary. The stars tidally break each other. Over time, the rotations of both stars synchronize with the orbital period, so that each star always shows the same face to the other. Many close binary stars are tidally locked, just as the Moon is tidally locked to Earth. For very close binary systems, where the stars are practically touching at the boundary of what are called their Roche lobes, mass can transfer from one star to the other. This mass transfer carries angular momentum with it. The star receiving mass can be spun up dramatically. This spin-up process is particularly important for neutron stars, which we will return to shortly. Young stars still in the process of formation, called T-Tauri stars for a prototypical member of this class discovered in the Taurus star forming region, are visibly surrounded by their protoplanetary disks in infrared observations. These stars are rotating fast as expected from angular momentum conservation during collapse, but many of them are rotating more slowly than conservation of angular momentum during free, full collapse would predict, which tells us that some mechanism is removing angular momentum from them during their early evolution. The leading mechanisms are magnetic braking and disk locking. Magnetic braking works through the young star's magnetic field. Young stars like the Sun have strong magnetic fields generated by convective motions in their interiors. This magnetic field couples to the ionized gas in the stellar wind, the stream of charged particles flowing outward from the star. The wind plasma is dragged along by the magnetic field lines as it flows outward, until it reaches the Alphen radius, the distance at which the kinetic energy of the wind equals the energy density of the magnetic field. At the Alphen radius, the plasma breaks free and continues outward on its own. By the time it breaks free, it is being flung outward with significant angular momentum that it carries away from the star. The star loses angular momentum to its own wind and slows. Disk locking operates through the magnetic coupling between the young star and its surrounding protoplanetary disk. If the stellar magnetic field is strong enough to thread through the inner part of the disk, it creates a connection between the star and the disk. If the inner disk is rotating more slowly than the star at the coupling radius, angular momentum flows from the star into the disk and the star decelerates. The disk acts as a brake. This mechanism can keep young stars spinning at moderate rates for as long as the disk is present, typically a few million years. Both mechanisms slow stars and both transfer angular momentum elsewhere rather than destroying it. Magnetic braking sends angular momentum into the stellar wind, which carries it out into the interstellar medium. Disk locking sends angular momentum from the star into the disk, where it becomes the orbital angular momentum of the material that will eventually form planets. The angular momentum extracted from a young star by these mechanisms is not lost. It is redistributed. It becomes the orbital energy of planets, or it is swept away into the interstellar medium by stellar winds, where it eventually contributes to the turbulence and rotation of the next generation of molecular clouds. Gyrochronology is the technique of estimating a star's age from its rotation rate, and it works because magnetic braking slows stars in a well-characterized mass-dependent way. Younger stars spin faster, older stars spin more slowly. The relationship between age, mass, and rotation rate has been calibrated against star clusters of known age, and can be applied to individual field stars to estimate their ages independently of other methods. The technique works because angular momentum conservation and the specific mechanisms by which angular momentum is lost produce a predictable trajectory of decreasing spin rate over a stellar lifetime. The Sun, rotating once every 25 days at its equator, and more slowly at its poles, is consistent with its age of 4.6 billion years on the gyrochronological sequence. When it was a newly formed T-Tauri star, it may have been rotating in less than a day. Over 4.6 billion years of magnetic braking and stellar wind loss, it has slowed by more than an order of magnitude. The angular momentum it shed is in the interstellar medium and primarily in the orbital angular momentum of the planets of the solar system. No one predicts that measuring how fast a star is spinning would give us its age, but angular momentum conservation, combined with the understood physics of how stars lose angular momentum through their winds, makes gyrochronology one of the most powerful age dating tools in stellar astrophysics. By the end of tonight, we will see that stars do not just lose angular momentum through these gentle mechanisms, they also gain angular momentum in sudden violent episodes, and the consequences of that gain are among the most extreme phenomena the universe produces. Now let us consider what happens when a massive star, far more massive than the Sun, exhausts its nuclear fuel. Stars shine by converting mass into energy through nuclear fusion. In the Sun's core, hydrogen nuclei fuse into helium, and the mass deficit between the reactants and products appears as energy. This process has been ongoing in the Sun for 4.6 billion years and will continue for another 5 billion or so. But more massive stars, those with more than about 8 solar masses, run their fusion processes far faster. A star of 25 solar masses burns through its hydrogen fuel in just a few million years instead of billions. When the hydrogen is exhausted, the core contracts and heats until helium begins fusing into carbon and oxygen. When helium is exhausted, carbon burns, then neon, then oxygen, then silicon. Each stage is shorter than the last and requires a higher temperature and pressure. Silicon burning, the final stage, produces iron and nickel. In the most massive stars, silicon burning lasts about a day. Iron is the endpoint. The iron, 56 nucleus, is the most tightly bound atomic nucleus in existence. Adding a proton or neutron to iron requires more energy than the reaction releases. Unlike every lighter element, you cannot extract energy from iron by fusing it with anything. When the iron core accumulates roughly 1.4 solar masses, it has no fuel left and nothing to support it against gravity. In less than a second, the iron core collapses, from a sphere roughly the size of Earth to a sphere roughly 12 miles across. The densities reached during this collapse are comparable to the density of an atomic nucleus, on the order of 10 to the power of 17 kilograms per cubic meter. To make that concrete, a single sugar cube of this material would weigh roughly as much as all the mountains on Earth combined. When the core reaches nuclear density, it stiffens suddenly. The infalling material bounces, and the bounce sends a shock wave outward through the rest of the star. The shock wave is assisted by a torrent of neutrinos produced in the collapse, roughly 3 times 10 to the 46 joules of energy carried away as neutrinos in just a few seconds. The shock wave blows the outer layers of the star apart in a core collapse supernova. The remnant is a neutron star, a sphere about 12 miles across, containing the mass of roughly 1 to 2 suns, composed almost entirely of neutrons packed to nuclear density. Now apply conservation of angular momentum. Before the collapse, the iron core was rotating at some rate. Estimates from stellar models suggest the cores of massive stars near the end of their lives may be rotating, with periods of anywhere from a few hours to a few days. Let us say the pre-collapse core had a rotation period of 10 hours and a radius of about 2,000 miles. The neutron star it becomes has a radius of about 6 miles. The radius is decreased by a factor of roughly 330. Angular momentum is proportional to mass times radius squared times angular velocity, and mass is conserved through the collapse. So the angular velocity must increase by a factor of 330 squared, which is roughly 109,000. A core rotating once every 10 hours becomes a neutron star rotating roughly once every third of a second. A core rotating faster produces a faster neutron star. A core rotating slower produces a slower one. No one expects this arithmetic to produce objects spinning hundreds of times per second. But neutron stars do exactly this. The fastest known neutron star, PSR JUM 748, 24/6 AID, rotates 716 times per second. Its equatorial surface is moving at roughly 24% of the speed of light. This is not a freak outlier requiring special explanation. It is what conservation of angular momentum predicts when the radius of an object decreases by a factor of 300 or more in under a second. The first pulsars were detected in 1967 by Jocelyn Bell Burnell, then a graduate student at Cambridge working under Anthony Hewish. The detection was initially so puzzling that the source was designated LGM-1, standing for Little Green Men, before the only physically plausible natural explanation was identified: a rotating neutron star, with a beam of radio emission sweeping around like a lighthouse beam, intersecting Earth once per rotation. The pulse timing was so precise and so rapid that it seemed almost artificial. It was not artificial. It was the most precisely spinning natural object ever detected. Pulsars are extraordinary clocks. The rotation of a neutron star is remarkably stable, decreasing by only tiny amounts over long timescales as the star loses energy to electromagnetic radiation and a wind of charged particles. The most stable pulsars, the millisecond pulsars that spin hundreds of times per second, maintain their rotation to within roughly 1 microsecond per year. This is comparable to the stability of the best atomic clocks. Millisecond pulsars spinning at hundreds of times per second are sometimes called recycled pulsars, and their origin is directly connected to angular momentum transfer between stars. A millisecond pulsar begins life as an ordinary pulsar in a binary star system. The pulsar was born spinning perhaps 10 times per second from the supernova of the original massive star. Over millions of years, the pulsar loses angular momentum to its electromagnetic radiation and slows. But the companion star in the binary system is aging. When the companion evolves off the main sequence and begins expanding as a red giant, its outer layers overflow the region where the neutron star's gravity dominates, called the Roche lobe. Gas from the companion begins flowing onto the neutron star. This accreted gas does not fall straight down. It spirals in, forming an accretion disk around the neutron star, just as any rotating and falling material forms a disk. The innermost gas in the accretion disk orbits the neutron star extremely fast. When it finally impacts the neutron star's surface, it transfers its angular momentum to the neutron star. The neutron star is spun up. Over millions of years of accretion, the neutron star goes from spinning a few times per second to spinning hundreds of times per second. Angular momentum transferred from the orbit of infalling gas produced one of the fastest spinning solid objects in the universe. The process is called pulsar recycling, and it is a perfect demonstration of angular momentum conservation operating between two bodies in a binary system. No one predicts that the evolutionary history of two binary stars would produce a neutron star spinning 716 times per second, with the timekeeping precision of an atomic clock. But the physics of angular momentum transfer from accreting material to a compact object is what the equations demand. The precision of millisecond pulsars has enabled an experiment that represents one of the most audacious endeavours in the history of observational astronomy. Pulsar timing arrays are networks of millisecond pulsars distributed across the sky, all precisely timed using large radio telescopes. The principle is this: a pulsar emits a pulse every few milliseconds with extraordinary regularity. We can model the expected arrival time of every pulse, accounting for the pulsar's position, proper motion, orbital parameters if it is in a binary, and the dispersion of radio waves in the interstellar medium. The residual timing, the difference between the predicted and measured arrival times, is sensitive to any effect that changes the effective path length between the pulsar and Earth. Gravitational waves do exactly this. A gravitational wave passing through our region of space slightly stretches or compresses the distances in the plane perpendicular to its direction of travel. When a gravitational wave passes between Earth and a pulsar, it changes the effective distance, and therefore the travel time of pulses by a tiny but calculable amount. The pattern of timing changes across an array of pulsars, specifically the correlation between timing residuals for pairs of pulsars as a function of the angle between them carries the unique signature of a stochastic gravitational wave background. In 2023, 4 major pulsar timing array collaborations reported near simultaneous results. Nanograv in North America, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Chinese Pulsar Timing Array all announced strong evidence for a gravitational wave background, a low, frequency hum of gravitational radiation pervading the universe. The signal matched the expected correlation pattern between pulsar pairs, called the Hellings-Downs curve, which is the distinctive fingerprint of a gravitational wave background, as opposed to any other correlated noise source. The most likely source is orbiting pairs of supermassive black holes at the centers of merging galaxies. Across the observable universe, countless pairs of galaxies have merged over cosmic time. When 2 massive galaxies collide, their central supermassive black holes sink toward the center of the merged system and eventually form a gravitationally bound binary, orbiting each other and radiating gravitational waves as they do. Each individual pair radiates gravitational waves too slowly to detect directly with current instruments. But the combined signal from all the merging supermassive black hole pairs across the universe produces a stochastic background in the nanohertz frequency range, exactly the frequency range that pulsar timing arrays are sensitive to. We detected the gravitational wave background from supermassive black hole pairs merging across the observable universe by monitoring the heartbeats of neutron stars whose spin rates are a direct product of angular momentum conservation during stellar collapse and angular momentum transfer during binary mass accretion. The chain is unbroken. Angular momentum conservation during the supernova collapse creates the pulsar. Angular momentum transfer during binary mass accretion spins the pulsar up to millisecond periods. The precision of the resulting clock lets us detect gravitational waves from merging black holes billions of light years away. No one predicts that the study of spinning neutron stars would eventually give us instruments sensitive enough to detect the gravitational echoes of the universe's most massive mergers across cosmological distances. But here we are. Neutron stars also come in a more extreme variety, magnetars. These are neutron stars with magnetic fields roughly 1,000 times stronger than ordinary pulsars, reaching strengths of 10 to the 14 or 15 times the magnetic field at Earth's surface. Magnetomagnetic fields are so strong that they influence the quantum mechanical structure of atoms, stretching them into elongated cylinders along the field lines. The vacuum of space near a magnetar is polarized by the field in a way that has been directly detected. In December 2004, the magnetar SGR 1806 released a burst of energy in approximately 1/10 of a second that exceeded the energy output of our Sun over the previous 250,000 years. The burst was energetic enough to partially ionize Earth's upper atmosphere from a distance of roughly 50,000 light years, detectable in global ionospheric monitoring systems. It was the most energetic event observed from outside the solar system in recorded human history at the time. The source of that energy was the rearrangement of the magnetar's intensely strong magnetic field, combined with the enormous rotational energy stored in the spinning neutron star. The spin of the magnetar, a direct legacy of angular momentum conservation during its birth in a supernova, was part of what powered the most violent electromagnetic event we have ever detected from beyond our solar system. By the end of tonight, we will have tracked angular momentum from spinning stellar cores to pulsars to the detection of gravitational waves. Every link in that chain is angular momentum conservation, operating at different scales and through different mechanisms. Let us now follow spin one step further inward, to black holes. When a neutron star in a binary system accumulates too much mass through accretion, or when the core of a very massive star is too heavy to stabilize as a neutron star, the collapse continues past the neutron star stage to a black hole. Like the neutron star, the black hole inherits the angular momentum of whatever formed it, and that inherited angular momentum changes the black hole fundamentally. A non-rotating black hole is described by a single number, its mass. Its gravitational field is perfectly spherically symmetric. It is, in the most literal mathematical sense, featureless. The only structure it possesses is the event horizon, the spherical boundary at a distance called the Schwarzschild radius from the singularity, beyond which nothing can escape, and the singularity at the centre where the density is formally infinite and the known laws of physics cease to apply. This solution to Einstein's field equations was found by Carl Schwarzschild in 1916, while he was serving on the Eastern Front in World War I. He completed it and sent it to Einstein from the front. He died of illness at the front a few months later. A rotating black hole is fundamentally different. It is described by two numbers, its mass and its angular momentum. The exact solution for a rotating black hole was not found until 1963, nearly 50 years after Schwarzschild, by the New Zealand mathematician Roy Kerr. The Kerr solution is not spherically symmetric. Its geometry is flattened at the poles and extended at the equator like a rapidly spinning fluid body, and it has a property with no equivalent in Newtonian physics or in the Schwarzschild solution. A rotating black hole drags space-time with it as it rotates. This is called frame dragging, and it is one of the most radical predictions of general relativity. In the vicinity of a rotating mass, space-time is not static. The mass's rotation pulls the surrounding space-time along with it, just as a spinning ball in honey drags the honey around it, except that what is being dragged is not a fluid but space-time itself. Near a slowly rotating body like Earth, this effect is real but tiny, amounting to a precession of a gyroscope's axis of less than 2 arc seconds per year in low Earth orbit. Near a rapidly rotating black hole, the effect is so extreme that it creates an entirely new region of space-time, with no analogue in any other context. This region is called the ergosphere. It surrounds the event horizon like an outer shell, extending farther from the black hole at the equator than at the poles. Within the ergosphere, the dragging of space-time is so strong that it is physically impossible to remain stationary relative to the distant stars, regardless of the direction or magnitude of any thrust you apply. You will be dragged around with the rotating space-time whether you try to resist or not. No one expects that the rotation of a black hole would create a region of space-time where you literally cannot stand still. But the Kerr solution is unambiguous on this point. Stationary observers do not exist within the ergosphere. The minimum orbital velocity imposed on you by the dragging of space-time is greater than 0. The ergosphere has a remarkable property. It lies entirely outside the event horizon. Objects entering the ergosphere can still escape, unlike objects crossing the event horizon. And within the ergosphere, it is possible to extract energy from the black hole itself. The Penrose process, proposed by the physicist Roger Penrose in 1969, works as follows. A particle enters the ergosphere on a specific trajectory and decays into two fragments. Under the right conditions, one fragment falls into the event horizon, carrying negative energy as measured from outside the ergosphere. The other fragment escapes. Because one fragment carried negative energy inward, the escaping fragment must carry more energy than the original particle did. The extra energy came from the rotational energy of the black hole. The black hole loses a tiny amount of angular momentum, and the escaping fragment carries that angular momentum away as kinetic energy. The total energy, momentum of the system is conserved. No energy is conjured from nothing. Angular momentum is transferred from the black hole to the escaping fragment. But the practical implication is that a rotating black hole is a reservoir of extractable energy bounded by its angular momentum. The maximum extractable energy for a maximally rotating black hole is roughly 29% of the black hole's total mass energy. For a black hole of 10 solar masses, this is roughly 3 solar masses of extractable energy, an amount comparable to what the Sun will radiate over its entire 10 billion year main sequence lifetime. This is not merely a thought experiment. A generalization of the Penrose process involving magnetic fields in the ergosphere, called the Blandford-Znajek mechanism, is the leading theoretical explanation for the relativistic jets of active galactic nuclei. When a supermassive black hole at a galaxy's center is surrounded by a magnetized accretion disk, the magnetic field lines thread through the ergosphere and are wound up by the rotating space-time into helical structures. These wound up field lines launch plasma away from the poles of the black hole at speeds approaching the speed of light. These relativistic jets are among the most energetic, persistent phenomena in the universe. The jet of the galaxy, M87, whose central supermassive black hole was directly imaged by the Event Horizon Telescope in 2019, extends for roughly 5,000 light years. The image, the first direct image of a black hole's shadow in history, showed a bright asymmetric ring of emission surrounding a dark central region. The asymmetry, the fact that the ring is brighter on one side than the other, is a direct consequence of the black hole's rotation. The side of the accretion disk rotating toward Earth is Doppler, boosted, making it brighter. The side rotating away is dimmed. The spin of the black hole is encoded in the geometry of the image itself. Measuring the spin of black holes is one of the primary goals of modern black hole astrophysics, and we have two main techniques. The first is X, ray reflection spectroscopy. Hot gas very close to a black hole emits X rays. Among those X rays is the ion K alpha emission line, a specific spectral feature produced by ion atoms in the inner accretion disk irradiated by energetic photons from above. The shape of this line is heavily distorted by relativistic effects. The extreme gravity near the black hole shifts it. The rapid orbital motion of the gas Doppler shifts and broadens it, and the strong gravitational field redshifts it. The detailed shape of the distorted ion line depends on where the inner edge of the accretion disk is. For a non-rotating black hole, the innermost stable circular orbit is at a fixed radius. For a rapidly rotating black hole, the innermost stable orbit is much closer to the event horizon. By modelling the ion line profile, we can infer the spin. Several stellar mass black holes have been measured this way. Cygnus X1, the first black hole ever confirmed, is spinning at very close to the maximum possible rate. GRS 1915 Plausible 5, a black hole in a binary system about 36,000 light years away, is also measured to be spinning rapidly. These high spins are consistent with formation from the collapse of a rapidly rotating stellar core, with angular momentum inherited directly from the progenitor star. The second technique is gravitational wave astronomy. When two black holes orbit each other and spiral inward toward merger, they radiate gravitational waves. The pattern of these waves, called the waveform, depends on the masses and spins of both black holes and on the alignment of their spins relative to their orbital angular momentum. When the spins are aligned with the orbital angular momentum, the in-spiral proceeds differently than when they are misaligned or anti-aligned. The LIGO and Virgo detectors have measured dozens of black hole mergers, and for many of them, the spin parameters can be constrained from the waveform. The first detection, GW1159014 in September 2015, was produced by two black holes of roughly 36 and 29 solar masses merging into a final black hole of roughly 62 solar masses. About 3 solar masses of energy were radiated as gravitational waves in under 1 second. The spins of both black holes were low. This is itself a piece of information. It tells us something about how these black holes formed, possibly suggesting they formed from stellar collapse in a binary system with specific evolutionary history. No one predicts that measuring the distortion of space-time by less than 1/10,000th the diameter of a proton would tell us the spin of black holes merging billions of light years away. But the angular momentum of the merging black holes affects the waveform in ways that are encoded in those distortions and that our instruments are now sensitive enough to read. By the end of tonight, we have traced spin from the solar system to neutron stars to black holes. At every scale, angular momentum is conserved, transferred, amplified by collapse, and revealed by precise measurement. Now let us follow it into the domain where it becomes strangest of all, the quantum world, where the very meaning of the word spin has to be renegotiated. Every particle in the standard model of particle physics has a property called spin. Electrons have spin 1/2. Photons have spin 1. Gluons, the carriers of the strong nuclear force, have spin 1. The W and Z bosons, carriers of the weak nuclear force, have spin 1. The Higgs boson, whose existence was confirmed at CERN in 2012, has spin 0. Quarks have spin 1/2. Neutrinos have spin 1/2. If the graviton exists, the hypothetical quantum carrier of gravity, it would have spin 2. These numbers were not measured by watching particles rotate. They were inferred from the statistics of particle behavior in magnetic fields, from the patterns of particle interactions, from the mathematics of quantum field theory, and from experimental techniques that we will describe shortly. The story of quantum spin begins in 1922, with an experiment so simple in concept that it was conducted in a modest laboratory in Frankfurt. Otto Stern and Walter Gerlach sent a beam of silver atoms through a carefully designed inhomogeneous magnetic field, one that was stronger on one side than the other. The purpose was to test whether atoms had an intrinsic magnetic moment, a tiny bar magnet-like property that would cause the atom to be deflected by the field. Classical physics made a clear prediction. A spinning charged sphere, if that were what an atom were, could point its spin axis in any direction. When it enters a magnetic field, its magnetic moment interacts with the field gradient and the atom is deflected. How much it is deflected depends on the orientation of its spin axis relative to the field. A random distribution of spin orientations should produce a continuous spread of deflections. Some atoms deflected a lot, some a little, and everything in between, producing a smear of silver atoms deposited across the detector plate. What Stern and Gerlach found was 2 discrete spots, not a smear, 2 spots. The silver atoms were deflected into exactly 2 groups, and nothing in between. The angular momentum of the silver atom's outermost electron, the electron that determines the atom's magnetic properties, could align in exactly 2 directions relative to the external field. Not 1,000 directions, not a continuous range. 2. This was incompatible with any classical model of a spinning sphere, which can be oriented at any angle. The result implied something new. The electron's angular momentum was quantized, meaning it could only take specific discrete values in any given direction, and specifically only 2. The value was exactly +1, half or -1/2 in units of the reduced Planck constant. The theoretical explanation came in 1925, when two Dutch physics students, George Uhlenbeck and Samuel Goudsmit, proposed that the electron has an intrinsic angular momentum of 1/2, which they called spin, and that this spin can point in one of two directions relative to any chosen axis. This explained the Stern-Gerlach result. It also resolved a long-standing puzzle in atomic spectroscopy. The fine structure of spectral lines, the way hydrogen's single emission line at a given wavelength was actually a closely spaced pair, exactly as required if the electron has two spin states with slightly different energies in an atom. But immediately there was a problem. If the electron's spin is a real physical rotation of a charged object, how fast does it have to rotate to produce the magnetic moment we measure? The answer, when you plug in the numbers, requires the electron surface to be moving at several times the speed of light. That alone makes the classical picture impossible. Worse, every experiment aimed at measuring the electron size has found it to be consistent with a mathematical point. An object with zero spatial extent. There is nothing to spin. There is no surface to move. Expectation. Quantum spin is a rotation, just a tiny one, and the word is literal. Reality. Quantum spin is an intrinsic angular momentum with no classical equivalent, carried by particles that may have zero physical size, arising through physics that has no classical description. The definitive theoretical treatment came in 1928. Paul Dirac was attempting to solve a problem that had troubled quantum mechanics since its formulation. The Schrödinger equation that governed quantum particles was not compatible with special relativity. It treated time and space differently, which Einstein's relativity forbade. Dirac wanted a relativistic wave equation for the electron, one that treated time and space on an equal footing. He wrote down the simplest such equation consistent with both quantum mechanics and special relativity. The equation had 4 components rather than the one of the Schrödinger equation. Those 4 components naturally described a particle with intrinsic angular momentum of 1, half that could point in 2 directions, exactly as Uhlenbeck and Goudsmit had proposed, together with its antiparticle, a positively charged particle, with the same mass as the electron, which was discovered experimentally 4 years later by Carl Anderson in 1932. Dirac was not trying to put spin into the equation. He was trying to make quantum mechanics consistent with special relativity. Spin and antimatter fell out of it automatically. They are not additional assumptions. They are consequences of requiring quantum mechanics to be compatible with the structure of space-time as Einstein described it. In a universe described by quantum field theory and special relativity, electrons must have spin 1/2. There is no version of the theory in which they do not. No one predicts that writing down a wave equation to reconcile quantum mechanics with special relativity would automatically produce electron spin, explain the Stern-Gerlach result, predict the existence of antimatter, and provide the mathematical foundation for all of quantum field theory. But that is what the Dirac equation does. Spin is not added to quantum theory, it is required by it. Now here is the structural connection between quantum spin and everything we have discussed at larger scales. Quantum spin is angular momentum, not analogous to angular momentum, not similar to angular momentum in some metaphorical sense. Actual angular momentum, obeying the same conservation law, conserved by the same Noether symmetry as classical angular momentum. In every particle interaction, decay, and creation event, the total angular momentum of the system, including both the orbital angular momentum of particles moving in space and the intrinsic spin angular momentum of every particle involved, is conserved exactly. This is not an approximation. It is not a useful fiction. The selection rules governing which atomic transitions are allowed and which are forbidden are expressions of angular momentum conservation at the quantum level. A photon has spin 1. When an atom emits a photon, the atom's angular momentum must change by exactly 1 unit to conserve the total. transitions that would require the atom's angular momentum to change by 2 or more units are suppressed, giving rise to the metastable excited states in atoms that are responsible for phenomena from laser-gain media to astrophysical emission nebulae. The spin statistics theorem then divides all particles into 2 fundamental categories with fundamentally different collective behaviours. Particles with half, integer spin, 1, half, 3, halves, and so on, are called fermions. Particles with integer spin, 0, 1, 2, are called bosons. Fermions obey the Pauli exclusion principle. No 2 identical fermions can occupy the same quantum state simultaneously. No 2 electrons with the same spin quantum number can be in the same orbital of the same atom. No 2 protons with the same spin can be in the same nuclear energy level. Bosons are not subject to this restriction. Any number of bosons can occupy the same quantum state simultaneously. The only limit on how many photons can be in the same state is the energy available to put them there. The spin statistics theorem, proved by Wolfgang Pauli in 1940, shows that this division is not a contingent fact about our particular universe. It follows necessarily from the combination of quantum mechanics and special relativity. In any theory that is simultaneously quantum mechanical and consistent with special relativity, half integer spin particles must be fermions and integer spin particles must be bosons. The connection between spin and statistics is not an empirical observation that happened to work out this way. It is a logical consequence of the structure of relativistic quantum field theory. No one expects the value of a quantum number to determine whether matter takes up space, but it does. The Pauli exclusion principle applied to electrons is why matter is rigid. Without it, all electrons in every atom would pile into the lowest available energy level. There would be no layered electron shell structure. Atoms would not combine to form distinct molecules with specific geometries. There would be no chemistry. Carbon would not have 4 valence electrons available for bonding. DNA could not encode information in a sequence of base pairs. Biology could not exist. The entire material world as we know it rests on the fact that electrons have spin 1, half, and therefore obey the Pauli exclusion principle. The Pauli exclusion principle applied to neutrons is why neutron stars do not collapse to black holes when their mass is below about 2 to 3 solar masses. Neutron degeneracy pressure, the quantum mechanical resistance of neutrons to being forced into the same quantum state, provides a pressure that resists gravitational compression. It is the same principle as the electron degeneracy pressure that supports white dwarf stars, applied to neutrons instead of electrons. The atomic clock precision of millisecond pulsars, which allow the detection of the gravitational wave background from supermassive black hole mergers, is ultimately grounded in the Pauli exclusion principle applied to the spin, 1 half neutrons that make up the neutron star. Bosons, freed from the exclusion principle, can pile into the same state in unlimited numbers. This is why lasers work. Vast numbers of photons in the same quantum state, coherently aligned, all with the same frequency and phase and direction. A laser is a macroscopic quantum state made possible by the bosonic nature of photons, which is made necessary by the fact that photons have integer spin, specifically spin 1. Bose, Einstein condensation, is what happens when a collection of bosons is cooled to temperatures close to absolute zero. The atoms, if they are bosons, or have been paired into effective bosons, suddenly all occupy the same lowest, energy quantum state, forming a macroscopic quantum object that behaves as a single entity. Superfluidity, the flow of liquid helium, without any friction or viscosity at temperatures below 2.117 Kelvin, is a consequence of Bose, Einstein condensation. Superconductivity, the flow of electrical current through certain materials with zero resistance below critical temperatures, involves the formation of Cooper pairs of electrons that couple through interactions with the crystal lattice and behave as effective bosons. All of these macroscopic quantum phenomena, lasers, superfluids, superconductors, Bose, Einstein condensates, follow from the bosonic or fermionic statistics of their constituent particles, and those statistics follow from the spin of those particles, and the spin of those particles is conserved by the same Noether symmetry as the rotation of the Milky Way. There is one more application of quantum spin worth noting, one that is closer to everyday experience than neutron stars or black holes. Nuclear magnetic resonance, which is the physical phenomenon underlying MRI scanning in hospitals, works because atomic nuclei have spin angular momentum. Protons have spin 1/2. In a strong external magnetic field, protons can be in one of two energy states depending on whether their spin is aligned with or against the field. Radio frequency pulses at a specific frequency can flip spins between these states. After a pulse, the spins precess around the field direction and emit radio signals as they do. By mapping which parts of the body contain which concentrations of protons, and by measuring how quickly different proton environments relax back to equilibrium, MRI produces detailed images of soft tissue without ionizing radiation. Every MRI scan performed in every hospital in the world today is a direct application of quantum spin angular momentum, the same property that Stern and Gerlach first detected in 1922, the same quantity that falls out of the Dirac equation as a mathematical necessity, the same thing that is conserved from the scale of quarks all the way up to the rotation of galaxy clusters by the same Noether symmetry, is what makes medical imaging of the human brain possible. The conservation law that governs spinning galaxies governs spinning nuclei. The symmetry is the same. The scale is different by roughly 40 orders of magnitude. The conservation law does not notice. Tonight, before we leave the quantum world, we want to sit with one more consequence of quantum spin, because it connects the most abstract physics we have discussed to something almost everyone alive today has experienced directly. The electron's magnetic moment, the strength of its interaction with external magnetic fields, is not simply what you would calculate from spin, 1/2 angular momentum alone. It is slightly larger by a factor called the G factor or gyromagnetic ratio. For a simple spinning charged sphere, the G factor would be exactly 1. The Dirac equation predicts a G factor of exactly 2 for the electron, but even that is slightly wrong. The measured G factor of the electron is approximately 2.2393 by 436256. That deviation from exactly 2, the tiny amount by which the electron's magnetic moment exceeds the Dirac prediction, is produced by quantum electrodynamics, QED, the theory describing the quantum behavior of the electromagnetic field. In QED, a real electron is constantly interacting with virtual photons, emitting and reabsorbing them in quantum fluctuations that change its effective magnetic moment slightly. The calculated correction, summed to extremely high precision, matches the measured value to more than 12 decimal places. No one predicts that the anomalous magnetic moment of the electron, computed to 12 significant figures and measured to 12 significant figures by entirely independent methods, would agree to within less than 1 part per trillion. But this agreement is the most precisely verified prediction in the history of science, and it rests entirely on the quantum spin of the electron. Tonight, quantum spin is not only a matter of abstract physics, it is also at work in the medical facilities of every major city on Earth. Nuclear magnetic resonance, the physical phenomenon underlying MRI scanning, works because protons have spin 1/2. When a patient is placed in an MRI machine, they are immersed in a strong magnetic field, typically between 1.5 and 3 Tesla, roughly 30,000 to 60,000 times the strength of Earth's magnetic field. In this field, the protons in the hydrogen atoms throughout the patient's body, in water molecules and fat molecules and proteins, align their spins either with or against the field. These two spin states have slightly different energies. A radio frequency pulse at precisely the right frequency, called the Lama frequency, flips the spins from one state to the other. When the radio pulse is switched off, the protons relax back to their equilibrium spin alignment, and as they do, they emit radio frequency signals. The rate at which they relax and the frequency of the signals they emit depends on the chemical environment of the proton. A proton in a water molecule in brain tissue relaxes at a different rate than a proton in fat tissue or in a tumour. By mapping the relaxation times across the body, MRI produces detailed images of soft tissue with no ionizing radiation. Every MRI scan in the world is an angular momentum measurement. The spin of the proton, 1/2 in units of the reduced Planck constant, is what makes the measurement possible. The same conservation law that governs the rotation of galaxies governs the precession of proton spins in a magnetic field. The scale differs by roughly 40 orders of magnitude. The physics is the same. Tonight, quantum spin has one more technological domain we should visit: spintronics. Conventional electronic stores and transmits information using the charge of the electron. Spintronics uses both the charge and the spin, adding an extra degree of freedom that can be exploited for faster, more energy, efficient computation and data storage. The hard disk drives that stored digital information for the past 3 decades, and the magnetic random access memory chips now appearing in computers and smartphones operate using a phenomenon called giant magnetoresistance, discovered independently by Albert Fert and Peter Grunberg in 1988, for which they were awarded the Nobel Prize in 2007. Giant magnetoresistance occurs when a stack of thin magnetic layers is configured so that the spin of electrons passing through the stack is either aligned or anti-aligned with the magnetic orientation of each layer. Aligned electrons pass through much more easily than anti-aligned ones, creating a large difference in electrical resistance that can be used to read out stored magnetic information. The information stored in a magnetic hard disk is ultimately quantum spin angular momentum, written in the orientation of magnetic domains on the disk surface and read out by the spin-dependent transport of electrons through a read head. The hard drive on which you might have saved files tonight, the memory chip in your phone, the magnetic sensor in your car, all of them are applications of the same quantum spin that falls out of the Dirac equation as a mathematical necessity. By the end of tonight, we have traced angular momentum from the rotational symmetry of space-time through the flat rotation curves of galaxies through the spin, up of neutron stars through the frame dragging of black holes and down into the quantum world, where spin is the reason matter holds together, the reason lasers work, the reason MRI machines can see inside a human brain, and the reason the hard drive in your computer can store anything at all. Tonight, every time you get an MRI scan, every time you use a computer or a phone with a magnetic drive, every time a laser pointer shines a dot across a wall, you are using quantum spin angular momentum. The same quantity, the same conservation law, the same Noether symmetry. Everything spins, and the consequences of that spinning go considerably further than orbiting planets. Tonight, quantum spin has one more surprise that we have not yet mentioned, and it is a surprise that shook the physics community in 1988 and is still not fully resolved today. The proton has spin 1/2. This has been known since the earliest days of nuclear physics, but where does the proton spin come from? The proton is not a fundamental particle. It is made of 3 quarks, 2 up quarks and 1 down quark, bound together by gluons, the carriers of the strong nuclear force. The quarks themselves each have spin 1/2. And for decades the assumption was straightforward. The proton's spin, 1/2, is simply the sum of the spins of its 3 constituent quarks. The European Muon Collaboration Experiment at CERN, known as EMC, tested this assumption in 1988 by firing a beam of high-energy polarized muons, which are particles with a definite spin direction, at polarized protons. The idea was to probe the contribution of the quark spins to the proton's total spin. If the quarks carried the proton spin, the interaction between the muons and the proton should show a specific signature reflecting the quark spin contributions. What EMC found was deeply unexpected. The quarks contributed only a small fraction of the proton's total spin. Depending on how the measurement was interpreted, the quark spins appeared to carry somewhere between 0 and 30% of the proton's spin, well below the nearly 100% that the naive picture predicted. The rest of the proton's spin had to come from somewhere. 3 candidates were identified immediately. The gluons that bind the quarks together also have spin, and there can be large numbers of gluons inside the proton at any moment, so the gluon spin could make a substantial contribution. The orbital angular momentum of the quarks and gluons moving around inside the proton, not their intrinsic spin but the angular momentum of their motion, could also contribute, and the C-quarks, the virtual quark, antiquark pairs that pop in and out of existence inside the proton due to quantum fluctuations could carry some of the spin. No one expects the spin of a particle that fits inside a space less than 1/1,000,000th of a nanometer across to be a puzzle that took more than 3 decades and counting to resolve. But the proton spin crisis, as it came to be called, launched an entire field of experimental and theoretical work that is still ongoing. The problem is not just experimental difficulty, though the experimental difficulty is genuine. The problem is that the angular momentum of a composite quantum system is distributed in ways that depend on the reference frame, on the energy scale at which you probe it, and on how you define what you mean by the spin of a constituent particle moving inside a larger bound state. The decomposition of total angular momentum into quark spin, gluon spin, quark orbital angular momentum, and gluon orbital angular momentum turns out to be ambiguous at a deep theoretical level. Different decompositions, each internally consistent, give different answers to the question of where the proton's spin comes from. This ambiguity is not a defect in the theory. It is a genuine feature of how angular momentum works in a relativistic quantum field theory. In non-relativistic mechanics, splitting the angular momentum of a composite system into parts is well defined and unambiguous. In a relativistic system, where particles are constantly being created and destroyed in quantum fluctuations and where the notion of a particle's location is blurred by quantum uncertainty, the decomposition is not unique. The relativistic heavy ion collider at Brookhaven National Laboratory in New York and the COMPASS experiment at CERN have been probing the proton spin structure for decades with increasingly precise measurements. The emerging picture is that the quarks carry roughly 30% of the proton spin, the gluons may carry another 20 to 30%, and the orbital angular momentum of both quarks and gluons makes up much of the rest. But the precise accounting remains uncertain. A future facility called the Electron Ion Collider, approved for construction at Brookhaven, is designed specifically to map the 3-dimensional structure of the proton, including its complete angular momentum budget, with unprecedented precision. When it begins operation in the mid-2030s, it will measure the orbital angular momentum of quarks and gluons inside the proton with enough precision to substantially narrow the uncertainties. This is a remarkable situation to sit with. We are able to detect the gravitational wave background from supermassive black hole pairs, merging billions of light, years away, measured through timing variations of less than a microsecond in the rotation of neutron stars. We understand the angular momentum of the Milky Way to the point where we can derive its origin in the quantum fluctuations of the first moments of the universe. But the angular momentum budget of the proton, a particle that has been studied intensively for nearly a century, and that we understand well enough to build nuclear reactors, still does not add up completely. The same Noether symmetry that governs the rotation of galaxies governs the spin of quarks inside protons. The conservation law is exact. The accounting of how that conserved quantity is distributed inside a relativistic bound state is one of the deepest open problems in nuclear physics. Tonight, every spinning thing in the universe conserves angular momentum perfectly. But understanding exactly where the angular momentum lives, at the quantum level, in the particles that make up everything around us, is a problem still being worked out. We want you to carry this with you. Physics is not finished. The same conservation law that Newton's successors described in terms of spinning planets is still being tested at the scale of quarks. The same Noether symmetry that governs the Milky Way's rotation is the same symmetry being probed at the relativistic heavy ion collider. The questions get more technical as you go smaller, but they are the same questions, asked at different scales, about the same conserved quantity. No one predicts that a physics experiment designed to measure how muons scatter off protons would reveal that we did not understand where the proton spin came from, and would launch 3 decades of experimental work that is still ongoing. But angular momentum is not a property that the universe makes easy to fully account for, even in objects we have been studying for a century. The universe conserves it precisely. Understanding exactly where it lives is another matter. Tonight, the proton spin crisis is one of physics' reminders that the deepest questions are not always the ones aimed at the larger scales. Sometimes they are aimed at the smallest objects, asking the most basic question: where does the spin go? We have followed spin from molecule clouds to neutron stars to electrons to the structure of matter itself. There is one final question we have not asked. We have established where the spin of individual object comes from. We have not asked whether the universe as a whole, the full observable universe, is spinning. In the standard cosmological model, the universe on the larger scales is isotropic. It looks the same in every direction. The cosmic microwave background, the afterglow of the hot early universe released when the cosmos was roughly 380,000 years old, is uniform to 1 part in 100,000 across the full sky. The large-scale distribution of galaxies and galaxy clusters, when averaged over volumes hundreds of millions of light years across, shows no preferred direction. Isotropy is one of the foundational assumptions of modern cosmology. The cosmological principle states that the universe is both isotropic, the same in every direction, and homogeneous, the same at every location. Together, these assumptions greatly simplify the mathematics and have been confirmed to remarkable precision by observations. A universe with a global rotation would be neither perfectly isotropic nor perfectly homogeneous. It would have a preferred axis, a direction in which the rotation is occurring, and the properties of the universe as seen from our location would depend on the angle between our line of sight and that axis. The observational evidence for isotropy is strong. The cosmic microwave background temperature is uniform to 1 part in 100,000 across the sky. The distribution of radio galaxies and quasars is statistically consistent with no preferred direction. The Hubble expansion rate, the rate at which galaxies are receding from us, is the same in every direction to high precision. But the evidence is not perfectly clean. In the detailed pattern of the cosmic microwave background, there are anomalies that have persisted through multiple satellite missions and that are difficult to explain within the standard model. The largest scale pattern in the CMB, called the quadrupole, should in principle be a roughly random orientation, but the quadrupole axis appears to be aligned with the axis of our solar system's ecliptic plane and with the direction of the CMB dipole, our motion through the universe, in a way that seems more orderly than chance would predict. This alignment has been called the axis of evil, a somewhat dramatic name coined by the cosmologist Kate Land, and it has been debated intensely since its discovery in WMAP data in the early 2000s. There are also hints of a hemispherical power asymmetry, with slightly more large, scale fluctuation power on one side of the sky than the other. The CMB temperature fluctuations on the largest angular scales are slightly weaker than the standard model predicts. Each of these anomalies individually is at low statistical significance. Cosmologists have devoted enormous effort to determining whether they are real, departures from the standard isotropic model, or the expected result of cosmic variance. The unavoidable fact that we can only observe one universe from one location, and there will always be statistical noise in any finite sample. Some researchers have proposed that a slight global rotation of the universe, too small to have been detected yet but detectable in principle, could produce some of these patterns. A rotating universe would possess a preferred axis, and the statistical properties of the CMB as seen from our location would depend slightly on the angle to that axis, producing exactly the kinds of anisotropies observed. In 2019, an analysis by Lior Shamir at Lawrence Technological University examined the handedness of spiral galaxies in large astronomical surveys and reported a slight excess of galaxies rotating counterclockwise when viewed from the northern galactic hemisphere. The excess was small, a few percent, and statistically at the boundary of significance. Other researchers have disputed the analysis, pointing to possible systematic errors in the automated methods used to determine galaxy rotation direction from images. The question remains scientifically open. A universe with a slight global rotation is not ruled out by current data. It is constrained to be very small if it exists, consistent with the high degree of isotropy we observe. But it is not zero with certainty. If the universe does have a slight global rotation, the implications would be profound. Noether's theorem connects angular momentum conservation to the rotational symmetry of physical law. A rotating universe would break that symmetry at the largest scale. The laws of physics would not be exactly the same in every direction. The conservation of angular momentum so precisely confirmed at every scale we have ever measured would be an approximation, valid locally, but not globally. There is a precedent for this kind of structure. The universe has a slight preferred direction in another sense, the matter-antimatter asymmetry. Our universe contains matter but almost no antimatter, even though the laws of physics that govern most interactions treat matter and antimatter symmetrically. This asymmetry, called baryogenesis, breaks the matter-antimatter symmetry of the laws of physics at the cosmological scale. A slight rotational asymmetry, a cosmic handedness to spin, would be a similar kind of large, scale violation of a symmetry that holds locally. By the end of tonight, we have traced angular momentum from the quantum scale to the galactic scale to the question of the universe's own rotation. At every scale we have measured directly, from the spin of electrons to the rotation of galaxies, angular momentum is conserved exactly, because the laws of physics are the same in every direction. Whether that conservation holds at the very largest scale, whether the universe itself is spinning or perfectly still, remains one of the open questions at the edge of what cosmology can currently reach. Let us return to where we started, because everything we have covered tonight connects back to a single answer. We began with a simple observation: everything spins, and we asked where that spin came from and why, after 13.8 billion years, it has never stopped. Tonight we followed spin through every scale of known reality. We started with the protoplanetary disk that formed the solar system, tracing how a barely detectable rotation in a molecular cloud was amplified by gravitational collapse into the flat, organized architecture of planets that we now inhabit. We saw how the Theia impact redistributed the angular momentum, giving us the Moon, and how the tidal interaction between Earth and Moon has been slowly transferring angular momentum from Earth's rotation to the Moon's orbit for 4.5 billion years, currently measurable to millimeter precision by laser pulses bounced off retroreflectors placed on the Moon's surface in 1969. We moved to the galaxy and found that the organized rotation of the Milky Way's 200 billion stars traces back to the asymmetric tidal field of the cosmic web that torqued the protogalactic cloud into spin billions of years ago. And we found that measuring the rotation of galaxies revealed dark matter, an invisible component of mass 5 times more abundant than all the visible matter in the universe, whose existence we first inferred from the fact that the outer stars of spiral galaxies were spinning too fast to be held in place by the gravity of the visible stars alone. We descended to the stellar scale and found that stars lose angular momentum through their magnetic winds over billions of years, slowing predictably enough that a star's rotation rate tells us its age. We found that the angular momentum of stellar cores, conserved through catastrophic gravitational collapse in supernova explosions, produces neutron stars spinning hundreds of times per second with the timekeeping precision of atomic clocks. And we found that the precision of those clocks allowed us to detect the gravitational wave background from supermassive black hole pairs merging across the observable universe. We explored rotating black holes and found that the angular momentum inherited by a Kerr black hole creates an ergosphere in which space-time itself is dragged around, and that the energy stored in that rotation can be extracted to power the most energetic, sustained phenomena in the observable universe, the relativistic jets of active galactic nuclei. And we descended into the quantum world and found that quantum spin, though utterly unlike classical rotation in its mechanism, is the same quantity conserved by the same Noether symmetry, and that the integer or half integer value of a particle's spin determines whether it obeys the Pauli exclusion principle, which in turn determines whether matter can be solid, whether chemistry can exist, whether biology can exist, and whether you can be here tonight to listen to any of this. We visited exoplanets orbiting distant stars in retrograde orbits, planets whose angular momentum has been redirected over billions of years by gravitational interactions with companion stars and sibling planets, confirming that the Kozai, lid-off mechanism and planetary scattering are as real and as common as our own solar system's gentler history would suggest. And we found, deep in the quantum world, that even the spin of the proton itself, a particle we have studied for nearly a century, does not yet fully add up, that the angular momentum budget of quarks and gluons inside the proton remains one of the deepest open problems in nuclear physics. The answer to where all of this rotation comes from is always the same. It comes from the fact that the laws of physics have no preferred direction. There is no special orientation in the universe, no up or down at the cosmic scale, no direction that the laws favour over any other. And because of that symmetry, angular momentum cannot be created from nothing, and it cannot be destroyed. The universe began with a certain amount of angular momentum. Not much, by any absolute measure. The initial rotation was tiny, a whisper, barely detectable against the random thermal motions of the gas in molecular clouds. But the laws of physics have no mechanism to eliminate it. Every interaction preserves it. Every collapse amplifies it. Every tidal force redistributes it, and 13.8 billion years on, it is all still here, in every spinning electron, in every rotating galaxy, in every neutron star beating out 716 pulses per second, in every black hole dragging its surrounding space-time around with it through the darkness. Everything spins because the universe has no way for things to stop. The conservation of angular momentum is not a rule that the universe follows reluctantly, one that could in principle be suspended. It is the mathematical shadow of the universe's most fundamental symmetry, the absence of a preferred direction, and the universe has been faithful to that symmetry for every moment of its existence. We are grateful you spent tonight with us. If this is the kind of exploration you come here for, we will have more for you. The link in the description will bring you back. We are here every week covering the cosmos, one question at a time, trying to make the science worth staying awake for even while we help you fall asleep. There is a kind of peace in knowing that the same law governing every spinning electron in your body governs the rotation of every galaxy we have ever observed. The universe keeps its books perfectly. The spin that existed at the beginning is the spin that exists now, redistributed, amplified, moved between objects by gravity and collision and tide, but never lost. Not once, in 13.8 billion years. Sleep well tonight. The universe is spinning faithfully right on schedule. Good night.